Homework 8, inverse functions, video 4. How to tell a function is not invertible. In other words, not one-to-one. Now, I haven't defined what one-to-one means yet, so I'm going to go ahead and define that now. One-to-one means equal outputs imply equal inputs. In other words, the only way two numbers can come out the same is if they went in the same. For example, f of x equals 2x plus 1, which did have an inverse and is invertible, is 1-to-1. Why? Well, let's pretend we put in two different numbers and get out the same answer. Let's call those numbers a and b. So we're forcing the outputs to be equal. Does this force the inputs to be equal? Well, our function says double and then add 1. So f of a equals 2a plus 1 and f of b equals 2b plus 1. Well, if we start stripping down one side by minusing 1 and then dividing by 2, it says that the inputs were equal. So equal outputs forced the inputs to be equal. Now, what about f of x equals x squared? Did that force, does equal outputs force equal inputs? Well, no, and I don't need to write it and I'll explain it. Can you think of two numbers that when you square come out the same? Two different numbers that when you square they come out the same. For example, when we square 3, we get 9. What else could we square and get 9? -3. So when we did f of x equals x squared, that is not 1-to-1. Because when I put in 3 and I put in -3, I get the same answers. They both end up being 9. But 3 is not equal to -3. Equal outputs did not force the inputs to be equal. So why is that so important? Well, think about what a function is supposed to do. Let's follow up on the f of x equals x squared. So we have f of 3 equals 9, and we have f of -3 equals 9. Well, the whole idea of an inverse function is to be able to take the answer and turn it back into the original input. So you did something to the 3 to turn it into a 9. If my function is invertible or 1-to-1, then the inverse should turn the 9 back into the 3. But what should the inverse do here? Well, here it turned the function turned -3 into a 9. If I were invertible, then my inverse function would have to turn 9 back into -3. Do you see a problem with this? I do. Functions can't do that. The definition of a function is every x has exactly one y. This x has two y's and it breaks being a function. Why did that happen? Because I was trying to undo a function that turned two different numbers into the same output. So no function will turn that one output back into two different inputs. Well, that's nice and all, but it's still kind of tricky to go, okay, but how do I answer this question? How do I tell if a function is invertible? Well, let's look at the graph of f of x equals x squared and see if we can visually see what went wrong. When I square 3, I get 9. Okay? But when I square -3, I also get 9. So the reason we have a problem is that we have these 2 points that are at the same level up. Let me connect them real quick. The 2 points where this horizontal line hits the graph of f of x equals x squared, these 2 points have different inputs, or different x's, but equal y's. That's a problem. Because no function is going to be able to turn 9 back into both 3 and -3. Functions can't do that. So visually speaking, the reason that f of x equals x squared failed to be invertible is because we could locate 2 points that had different x's but equal y values. So if one function turns 3 into 9, but also turns negative 3 into 9, then the inverse function has to simultaneously turn 9 back into 3 and 9 back into negative 3, but functions can't produce 2 outputs at once. And so we had a problem. So visually speaking, there is a way to look at a function and go, you're not invertible if I know what your graph is. And that way is called the horizontal line test. And it goes something like this. It's like the vertical line test, which answers the question, are you a function? The horizontal line test answers the question, is a function invertible? If a function's graph can be intersected more than once with a horizontal line, comma, then the function is not invertible. Excuse me. I have a computer over here on the side with your homework open so that I can scroll through it while I'm doing these videos to make sure that I'm not missing anything, and it just went to sleep. Okay. So this gives us a real quick way to look at a function's graph and go, you're invertible. So for example, consider the function g of x equals the square root of x. Does that graph not pass the horizontal line test? If I hit it with a horizontal line, I'll only hit it once, no matter where I draw it. By the way, the converse of the horizontal line test is also true. If you can't hit it more than once, then it is invertible. So it's two-way conditional. So this is weird because we're saying that f of x equals x squared is not invertible, but this function is. Wait a minute, how can one of them be invertible but not the other? What's the inverse of square rooting? Squaring? No, because we just said squaring is not invertible, so how could it be the inverse of anything? Well, it's squaring, but sort of. There's another piece of the puzzle I haven't shown you yet, and it's the relationship between the function, the graph of a function, and the graph of its inverse. And we'll show you that in the next video.